Lesson 74, work. So today we will discuss the concept of work. Now, this concept of work is actually a part of a much broader idea, and which has got to do with energy. And we're not going to discuss all the factors of energy today. I was looking over the book and like the things that they expect to talk about with energy, and it was just a lot. So I thought, well, let's just do a small snippet today, and we'll leave all the hard stuff about energy and stuff till next week. So we'll just do work today. Well, what did we do earlier this week leading up to this lesson? On last lesson, Thursday, what we did was we looked at, and before that, we'll talk about Tuesday's lesson, we looked at torque. So the start of the week, we were discussing how we can imagine net torque on an object. And what we did was we calculated net torque, we dealt with net force, and then we moved and we did some calculations, and then what we did was we finished that. We looked at structures, how structures use torque. And we also looked at how a sign might, exhibit torque, and looking at the forces acting on that as a structure. We wrapped this. We then moved on to our next topic, which is collisions. Now we've already done a whole lot of stuff on collisions, so I'm not going to. I said to you guys, I'm not going to spend time reteaching that. I'm just going to quickly re-go over it, and then I'll quickly talk about directions. So what we did was we did this quick question here, which is what we did it, which is a truck crashing into a car, but they're going in opposite directions. Today, what we're going to talk about is work. Now, work is, believe it or not, something we've already discussed. We've already studied work, and if you got the picture on the right here is actually a picture taken. The picture on the right is actually taken from a slide all the way back in term 1. We discussed work already when we looked at thermodynamics. If you actually read on the tiny little screen on the bottom right here, work, which has the symbol W, is work as a measure of the energy transferred to an object when as an object is forced over a distance. And that is actually the same thing here we're going to talk about. We're going to talk about an object being forced over a distance. In this case, we talked about when a popcorn bag expands, it does work because it pushes against the bag. It applies a force against the bag, and that is that was an amount of work, and that was energy being lost from the system. And then we talked about what happens if you got a plunger and you push that plunger down into a system which has a bunch of air, and how that would do work on the system. And then we did a whole big test about that. And of course, Paul, Vince, and Jason have no idea what we're talking about because they weren't in class when we studied this. But we can really talk about that. Work is a measure of the energy and is linked to force acting over a distance. We can actually calculate that by work equals force times displacement. It is a force over a distance, S being our displacement, because we use, S equals U squared plus V squared equals U squared plus 2AS. So work is an idea of a force over distance. There are actually 2 units that we can give for force. For work, we can give it the units joules, which is what we used in term 1, or you can give it the units Newton meters, because that's what it's measured in, Newton meters. Now, I was going to put up here whether or not work is a vector. And to be completely honest with you guys, I'm going to be very candid here. I don't know. I'm going to say, why don't I know? Because work is measured in joules. Joules is energy. Energy does not have is a non-vector quantity. But Newton and meters are both vectors. So I actually don't know whether work is a vector. I probably could have spent like 20 seconds Googling it before this class, so I didn't look like an idiot. But I don't know. I'm sure someone else here can look it up, and then they can be the smart one that says, actually, sir, work is not a vector, or work is a vector. I don't know. I will have an answer for you next lesson. But at the moment, it's a mystery. So that's all we really need. That's the basics of work. That's a formula for it. So there, sometimes that formula as well is given as work equals FD, a force over a distance. We're going to use S because it means displacement, but yeah, you can just use FD if you want instead. We're going to do some basic calculations, and then we're going to do some more advanced calculations, and then we're going to wrap up at the very end by saying, what does this mean? Why is work like? One of the things that I've tried to do a little bit is I've tried to say, you know, great, this is the formula for torque, this is the formula for momentum. Great, cool, but why? And then how do we use it? This is how we use it. And at the very end, I say, why do we need it? It's, you know, there are a bunch of random measurements out there that we don't actually need. So what does it mean? Why do we use it? Work is great because essentially, and I'm going to cover this later, because it deals with energy. Let's grab, speaking about energy, let's look at Arnold Schwarzenegger, more energy. A weightlifter is lifting 50 kilograms from the ground. This, I believe, is known as a deadlift for those of you that are proper gym nuts. But yeah, to above his head. If the maximum height the weight reaches is 1.9 meters, how much work has the lifter done? Well, let's work out how much work the lifter has done. Work equals a force over a displacement or a distance. The force in this case is it's a 50 kilogram mass. So that force is going to be 50 times 9.8. So that's going to be about 490 something. I was right, 490. So that's 490 newtons worth of force. And that force is because it's going to be gravity, it's going to pull it down. So we need to move that 490 newtons worth of force over 1.9 meters because that's our displacement. So therefore, 490 times 1.9 equals 931 joules, or 931 Newton. Actually, I'll do a capital N, Newton meters. And that's it. Now, of course, if you had the opposite, we could work backwards. We could say, oh, a particular strong person can do 1,000 newtons, 1,000 joules worth of work. How much can you work this out? You might think to yourself, that doesn't actually sound like a very big number. And that is correct. There probably isn't a huge number, but you've also got to really, I guess one of the things you should play into account is how quickly are you expending that 931 joules? It's very easy to do 931 joules worth of, or to use up 931 joules worth of energy if you're doing it over a very, very slow time. But if you're picking this up really quickly, that can be pretty high. So yeah, that's how I sort of think about it. That's just the basic sort of equation here, and I think I'm pretty sure I got all this correct. So yeah, that's how you would calculate energy. Now the example from the book involves like doing net force and like looking at, I think it's got to do with a object which is being pushed to the right and it's net force, but it's got a force of friction to the left. And so what you can do is you can look at the net force, and they did, well, what's the work of the net force? What's the work of friction? What's the work that they're pushing? And all that is just finding out these individual forces. We're not going to do that here, but you could do that. You can, I'm going to give you guys can look in your textbooks if you want to see a different interpretation, a different way to do this type of question. What we're going to do is we're going to do another example. We're going to look at this example here. And again, if I'm going too quickly, please stop me. I'm actually trying to go relatively quickly so you guys can have a chance to work with some questions, but we're going to look at this guy here. This is another very similar to almost the attendance question. A car is forced to come to a quick stop. So maybe and put on its brakes before crashing. Put on its brakes before crashing. Yep. Yep, okay. And I used the right form of it, so I was just double checking there. If the car was initially traveling at 22 meters per second and stopped in 10 meters, it stopped in 10 meters. Stop there. The mass of the car is 1,200 kilograms. We've got 3 questions here. What is the car's deceleration? And actually, you could actually do this question using, again, you could actually do this question using impulse, but no, you couldn't, because they haven't given you a time. What is the net force of friction acting on the car? What is the work done over this distance? Okay, so let's do this first one. What is the car's deceleration? Well, we're looking for A. We've been given a final velocity of 0 because we come to a stop. We've been given an initial velocity of 22 meters per second. I chose 22 meters per second because that's roughly around 80 kilometers an hour, and so I wanted this car to be going pretty quickly. But I could have said 27 meters per second, which is about 100 kilometers an hour. I've been now writing these questions so much that now I've started to think of speeds in meters per second. So when I'm driving 60 kilometers an hour, I think in my head, I am doing about 17 meters per second. It's kind of weird. It's a very weird way to think about things. And you guys won't experience this unless you decide to become a physics teacher yourselves. And it stops in about 10 meters. So there we go. There's a value of S. S equals about 10. So we're going to use the formula, what has V, U, S, and A in it. We're going to use V squared equals U squared plus 2AS. V squared is 0 plus U squared is 22 squared plus 2 times A times 10. 22 squared, 484. So it's going to be negative 484 equals 20A. I've skipped a couple of steps there, but hopefully you're okay with me moving this 22 squared over to the other side, and then 2 times 10 is 20. So therefore, A is going to be negative 484 divided by 20, which should give us 24.2 meters per second squared, negative, sorry. And that makes sense that it's negative because it's slowing down. I think I must have got this wrong when I did this last time on my own, so I'm glad that I've redone it with you guys. So that's the acceleration. We can give ourselves the net force, because now we have an acceleration. We can go F equals ma equals negative equals 1,200 times 24.2 equals, well, someone's saying stop, sir. Yep, no, they've given me an answer. Thank you. So I can double check to make sure that I've got the right one. 29,040 newtons worth of force, or so that's going to be backwards. That's going to be our force of friction here. And we've got one more question here. The last question here is in green. What amount of work is done over that distance? So work equals force multiplied by distance equals 29,040 times our distance, which is 10 meters times 10 is going to be 290,400 Newton meters, or 290,400 joules. You don't need to give both. I'm just giving both in case you guys want to know both. And that's it. That's how to do this question. Before I move on though, if you guys will indulge me, I would like to spend a minute just doing some random stuff. I would call this riffing if you were, if I was a, a rapper, which I'm not, but I want to quickly show you guys. I'm going to do this over here. This is, actually, I'm going to rub this out first. What I'm going to do is I'm going to say, firstly, this is not, what I'm about to do here is not necessarily something you need to know how to do for this topic, but I just want to show you some interesting things that we could do with this. I'm going to bring in some facts here. I know that energy, or Q, which is the amount of energy that enters the system, is equal to mc delta T. And you might be saying, whoa, 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 this is from term one. I'm like, yes, this is term one. I'm only going to spend about a minute riffing on this, which is just going to be doing some random calculations. So if you don't understand this, that's fine. What I'm going to do here is I've actually brought in some random statistics that I've got here. If I know that the specific heat of rubber, is 2000. And I know the mass of one particular tire is usually 7.2. I looked that up. I said, well, how much does a tire weigh? A tire can weigh anywhere between 7.2 kilos, 10 kilos. It can weigh as little as 6 kilos. So I thought 7.2 was the first answer I got. So I wanted to do that. So what I want to do is I want to say, well, what is the change in temperature? How hot are these tires going to get? Now, you might say, okay, so let's take that answer. Let's put 290,400 in. And we could do times 7.2, but I would say no, because there are 4 tires. So what I actually need to do is I need to change that 7.2 into 28.8. There is 28.8 kilograms worth of rubber that is going to experience that friction against the road. So if I actually do this, if I go 290,400 divided by 28.8 times 2000, I can actually find out how much hotter the rubber in the wheels would get. So I'm actually going to do this here because I'm like, why not? If you guys are following along, great. If you guys are now completely lost, and again, if I was Jason or Vince who missed out on term one, you guys have no chance of understanding what I'm doing. But 28.8 times 2000, by doing all these calculations, I actually get a value of 5 degrees. And that is an increase. So that's an increase of 5 degrees. So that means that if you measure the temperature of the tires, you could actually feel each tire getting 5 degrees hotter. There is a lot of assumptions that I've made in doing this calculation. What I've assumed is that I've got the correct version of rubber. I've assumed that it's 7.2 kilograms. It could be less. I've also assumed that the whole tire gets that 7.2. Very unlikely the whole tire is going to get that energy, because that energy is probably only going to apply to the surface of the tire, not the whole tire itself. So then therefore that would make it a hotter value. And of course, there could be other forces at play as well. It might not be acting on the whole tire as well. It could be just acting in the middle of the tire. But just, I guess, why did I waste my time doing that? I guess I wanted to show you that all physics and science are related in some ways. I also wanted to show you, hey, we've already got this skill, so let's just pop it out. Just as a quick thing, just to say, hey, this is actually a skill that there was a lot of questions at the start that I had to ignore and not give you guys, because it requires you guys to have an understanding of work from a motion perspective. But now that you guys have got that, I thought, well, you know, let's just throw it in there. But you don't need to know that if you're like, oh my God, hyperventilating. I just thought I would just quickly do something interesting like that. Something to make you think outside the box. I'm going to finish up on 2 quick slides, and then that's going to be it. These 2 slides are what I would call the implications, which is what I would really think of, you know, I really think of these being a little bit like, so what? You know, what I want to give is like, what, so what? Now you're given as a brand new term, like work. Why do I care about work? Why should I care about work? I wanted to give you guys a quick example here. And I actually think about this a lot when I'm walking around the school, going from subtopic to topic to teach different subjects. I weigh about 100 kilograms. Yeah, I could lose some weight. If I need to go up 1.5 meters to a classroom, let's say that I'm trying to get into D block, or maybe the doctor's portable, or what's another room that's got a ramp on it? I think like D10 has got a ramp on it. But yeah, if there's anything like this kind of classroom, what do I have here? If I weigh 100 kilos, if I go F equals mg, I've got 100 kilos times 9.8. That's going to be about 980 newtons of force that has to be expended. Now, if I walk up these stairs, right? Let's say those stairs are 2 meters, yeah? So what I need to do is I need to go work equals 980 times 2 equals 980. And you might say, why is it not 1.5? Because it's a hypotenuse here, ladies and gents. But even then, I haven't measured it like exactly. But yeah, we'll go with 980 times 2, that's 1,360 joules. That's how much energy I would need to go up the stairs. But I've got a question here. What if I went up the ramp instead? That ramp is a lot longer distance. That's 5 meters worth of distance, maybe more. But we'll call it 5 meters because, you know, whatever. It's at least double the length. So let's do that. Well, what's the work this time? It's the same force, but now it's the same, well, sorry, I've actually done this question wrong. I'm going to apologize straight up. I need to go up 1.5 meters. So that means I've actually done this question the wrong way around. I apologize for that. I need to go up 1.5 meters. So I'm going to go 980 times 1.5. I should have rehearsed this before I did the lesson. I apologize. That's 1470 joules. Now, there are 2 ways I can get that 1470 joules, and I can work out how much force I'm going to need to do that. I can either use up the energy for that by going up the stairs, or I can use it up by going up the ramp. Okay, let's see if I can get this correct this time. I think I've still got this wrong, ladies and gents, but I'm going to try and explain it. The idea is this. If I've got 1470 and if I go force times the distance that I need to travel, if I put that 1470, if I go up the 2 meters of stairs, then that will tell me how much force I'm going to need. 1470 divided by 2 means that I'm going to have to exert 735 newtons if I take these stairs. But if I take the ramp, right, I'm still going to get 470 joules because I'm going up 1.5 meters. It's still that 1.5 meters, but now I'm going to do that over 5 meters. If I do that over 5 meters, 1470 divided by 5, I only need to apply 294 newtons. That's a lot less. I actually have to apply less force. Now you might think to yourself, okay, how does that work? The trick is that even I actually have to apply less force, which just means that what I'm doing is I'm actually applying less force compared to this one here, and that's because these distances are different. What I'm doing is I'm still doing the same amount of work. I'm just doing that work over a longer distance. Essentially, I need to apply that 294 newtons over a longer distance. You can almost think about that as, yes, I can take the ramp. The ramp will be easier, but what do I lose? I lose time. It's going to take longer to walk up the ramp than the stairs. It would be even shorter to climb up a ladder, which would be just expending the straight up 980 joules, just to 980 newtons to lift myself up. The longer the ramp, the less the amount of force that I would need. So what work does is it gives you a way to understand different ways of expending energy. The last example or implication that I like to talk about is this one here, taken from a year 7 sort of idea. If I have two levers, and I hate teaching levers to year 7s in that because I can't really explain to them in a good way how to understand them. But now that you guys are in year 11 physics, I can. If you guys think about this, right? If I want to lift this 10-kilogram block, I need to push down on this lever. And that's a very, and so therefore that's going to be a force, and I'm going to be able to apply that force over a certain distance s. So because that s is very, very small, I need to apply a lot of force because it's a very, very small s. So it's going to be really difficult to lift this up. And you guys might know that if you've ever tried to open one of those tin cans and it requires a lot of force because it's very small, you can't really open something with, if you have to try to open something, you can't get it open because your fingernails are too short. That's what we're talking about. But if I compare this to lifting it in this case, I have to move a much larger distance. In this case, our S is very large and our F is very small, but we still get the same amount of work. Let's pretend if this was 10 centimeters, so 0.1, and this was 1 meter, I would need to, and let's just say we need to get, let's just go randomly, we'll go 100 joules. If I want to get 100 joules, I need to apply 100 newtons worth of force here. But here I need to apply 1,000 newtons worth of force. That is a much larger value. And that's because I don't have this distance. Yeah, sure, I have to apply that 100 newtons over 10 times the distance, but it's going to be easier to push down with 100 newtons compared to trying to push down with 1,000 newtons. And that's how levers sort of can be thought of as a work. It's like a distance versus force trade-off. You can get the same amount of energy, but you have to apply that smaller force over a longer distance. And that's how I sort of think about that in terms of what's going on here with regards to why work is so important. It's a good way for us to talk about energy and how we can, get the same job done, use the same amount of energy, but do it in different ways. Ladies and gents, there's about 10 minutes left of the lesson. What I'm going to ask you guys to do in this last 10 minutes is to continue working on 11.2. I haven't given you guys much time in class to work on 11.2, so I'm going to give you guys some time now to work on 11.2. What you don't get done, I'd like you to start working on at home on your own as homework. So I'm going to set this as homework. I'm going to make this due probably by next Tuesday, which is the double period, because then I'm going to start relying on you guys knowing this. If you do want to know though, for question 1 where it says the astronaut, how do astronauts move around? What they do is they have little gas canisters in their suits, and those gas canisters can push out air. And as that gas canister pushes out air, that air is going to push back on the astronaut and move them forwards. Or you could think about it as the conservation of momentum, as to conserve. If this is being pushed out backwards, then the astronaut's going to have to be pushed out forwards. You could also answer this question as well as if the astronaut pulls on the rocket and pulls backwards, in order to compensate for that new momentum going backwards, the astronaut has to move forwards. Again, and that will compensate, making the net momentum equal 0. The momentum initial final equals 0. You can think about that as also being another explanation of Newton's third law. I'm going to give you guys the next 10 minutes to work on that, and then I'd like you to do the rest of it for homework. I'm going to keep the Zoom open in case you have additional questions. I'm going to apologize for butchering that first example, but I'm glad that we got through there in the end.